Hello again. My name is Kevin Hoyt, and I'm the Developer Advocate Lead for Emerging Technologies at IBM. In the previous part of the series, I introduced blockchain concepts. I laid out some guidelines as to when it should be used as well. In this part of the series, I'm going to cover how blockchain works from a developer perspective. We'll examine smart contracts and how to connect to them from web clients, and we'll even take a blockchain-powered application for a test drive. Now, since we're getting a little more specific, it's important to note that blockchain is an open source technology. There are many implementations out there, but from here on out, when I refer to blockchain, I'll be specifically referring to the Hyperledger Fabric implementation run by the Linux Foundation. Now, if we continue to think of blockchain as a distributed database, then smart contracts, which are also referred to as chain code, are effectively the equivalent of stored procedures. Now, chain code is written in Go, it's compiled, and then deployed to the blockchain. In the case of Hyperledger Fabric, the preferred means of deployment is actually from a public GitHub account. You tell Fabric where the repo is, and then it goes out and fetches it and works the deployment for you. Now, the chain code is what actually works with the block data itself. It's the business logic. You can think of it in that way. It's responsible for actually committing the transactions. So there are three main methods you need in your chain code. The first one is an init function, and this gets called automatically just after the deployment is complete. This is the place to do any kind of storage initialization that your application needs. In this snippet, I'm taking an empty array of account structures, and then I'm converting it to JSON and placing the bytes of that JSON string into a block with the key of accounts. So in this way, I'm instantiating and initializing an array of accounts for me to be able to reference when I call the other methods. The invoke function is for client transactions that don't expect a return value. So calls to invoke may take some indeterminate period of time to execute and complete, right? Because they have to achieve that consensus and they have to be spread across the distributed network. So that takes time. It may take milliseconds, it may take longer. So the call to an invoke function will immediately return with a transaction number, but no other real data. Now, this is usually a good place to put your kind of create, update, and delete operations, because you functionally have a copy of that record already with you when you're submitting those values. And so you don't really need to worry about when that piece of data is actually transacted against the blockchain. In this snippet here, this is an example of the invoke function. You'll see that one of the arguments that comes in is a function name. It's a string value here called function. And we evaluate that function name to map to an actual function we want to call within the chain code. So in this case, if the requesting client said account create, then function would equal account create, and then it would return the response from invoking the account create function within this chain code. All the three core functions take an array of strings as arguments as well. You might choose to send just one string, for example, and that might be just the JSON value you want to store, or you might choose to send a series of values that you want to map to specific data structure inside of the chain code. The choice is really yours. In the end, the data stored on the blockchain is an array of bytes. That's it. Now, you could even send a legal document, for example, or an image. Those files are generally kept off the blockchain in a separate data store. But what is kept in the blockchain, in the case of those digital binary kind of files, is a hash of the file that's stored in the blockchain. So in this fashion, if somebody requests access to that legal document or image, you can rehash it, check it against the hash in the blockchain, and verify that it hasn't changed since it was stored. And then you can go ahead and do whatever transactions you need to do to that data. So if you're sending any kind of array of strings, this is a good little snippet here just as a point of reference that you might use for building JSON. In this case, we'll take arguments 0 and 1, which will be the ID and the first name, and then we'll make the variable content, which will be the complete JSON string, and then we'll go ahead and marshal that complete JSON string into an account data structure instance. And then we'll go ahead and append that to some larger number of accounts in the system, and then we can go ahead and marshal it back from the JSON string, in this case, from the native data type of accounts into an array of bytes, JSON string bytes, and put that back into the blockchain. So this is just a snippet I've included for those who prefer to send the individual arguments and have that work done on the chain code rather than sending the prefab JSON string that you want to commit. So the third function that we talked about, so we talked about init, invoke, and then the third one is query. So the query function is designed to return some amount of pertinent data. So this is where you want to do query operations, right? This is the various find actions that your application might require. So in this example, if the function name that's coming in is account by ID, then we'll invoke account by ID. We'll pass it those pieces of information and look that information up. So here's an example of reading all the account records in the blockchain. You might start to see abstractions that can be made here as well. So for example, the key that is used to say where the value is being stored could be passed as one of the strings functionally. That would simplify the code complexity in that you would just need to implement CRUD functions once, period, and then be able to handle all different variety of data structures. At the same time, you might see how at this point you can send one string with the corresponding JSON already formatted for storage. Again, these decisions are really left for you, at least as far as blockchain is concerned. Right? It's just an array of bytes as far as blockchain is concerned. So how you approach this is really going to be depending on your smart contract, your business needs, your business logic, that is, and how you want to implement it for your system. Now, Hyperledger Fabric supports cross-origin resource sharing, or CORS, which is a web standard and that allows the browser to request data from a server that the page didn't come from. Right. So CORS is supported by more than 95% of modern browsers, at least at the time of this writing. So it's a well-adopted capability. And what happens is when the page that's in the browser goes to make a request for data that's not up from the same server, there's actually a pre-flight request that goes out to the desired endpoint. And then should that server be okay with this kind of cross-domain sharing, then it goes ahead and sends a pre-flight response that says, yep, we're good from this URL with these operations. And that all happens in the background as soon as you go to make for example, your XHR request, your XML HTTP request. So by the time the XML HTTP request actually happens, this pre-flight has already happened and exchanged, and then you can go ahead and make your request, and it happens effectively transparently to you, but it's a really big deal because allowing the browser to talk to other APIs on other servers is an important aspect of how we compose our applications. So the result of Hyperledger Fabric supporting CORS is that there's really only two different types of requests that we need to implement from a JavaScript perspective. One to call the invoke functions, right? So you want to create, read, and delete. And and one to call the query functions for find, by account ID or what have you. Now the parameters only differ slightly. So the call to the invoke function in your chain code, what you do is here in the method attribute, you specify invoke. And then you provide the chain code ID. Now this is an ID that will be given to you when you deploy chain code. It will give you an ID that says, yep, here's a specific one you're working with. So you'll put that chain code ID in here. And then you'll also specify the function name that you want to call. Remember in our Go code, in our chain code, we had that parameter come in, that argument with the function was a string. Well, that's this guy right here. So in this case, the function is account create. And then remember that the rest of it was an array of strings. Well, that's exactly what we have here. So here the arguments, in this case, the ID would be ABC-123, and the name would be K.R. Hoyt. Now, calling the query function of the chain code is only slightly different. In place of invoke as the method, we'll specify query as the method. And that's it. That's pretty much the only difference. You might choose to wrap these in a promise or leverage the async await functionality of ES6. If you kind of wrap all that up, you have a really nice service controller ready to go. Leverage that from your application and communicate directly to Hyperledger Fabric, storing and accessing data on the blockchain. So that's it. That's all there is to performing create, read, update, and delete operations against Hyperledger Fabric. Now, I want to take a moment to show you an application that is running on Hyperledger Fabric that is a web application. So let's go ahead and take a look. All right, so this is Toodles. Toodles is a blockchain-powered to-do list. A little bit of architecture. It's built using Polymer as a polyfill, specifically Polymer RC release for version 2. And Polymer is used as a polyfill here, in this case, for the various web component standards. The entire application is delivered here. It's also written in ES6. I should clarify as well. So Toodles, when we go to the Toodles URL and it loads up, we're presented with a login screen. So I can log in here as K.R. Hoyt. And we'll go ahead and log in. And I've left the debug, the developer console open here for us to be able to see kind of the things that are going back and forth. So when I logged in there, I was sending a query command, a query request to the chain code, invoking that query function in my Go code, and then passing on the respective commands to be able to find a login that matched a specific user. So in this case, for example, if I log out here and I enter the wrong password, say ABC and not ABC123, which is the password in this test case, say, okay, log in, and it comes back and says, oh, not logged in, you see here. So that, in this case, I've sent the username and password arguments again to that query function in the Go code on blockchain via XHR. And it's gone ahead and tried to find an account in the blockchain that maps to the username and password that I provided. It can't find any, and so it sends the corresponding response. And then the browser gets that response, and it shows that we're not logged in. So now let's go ahead and put the right username and password in here, and we're logged in. Now the data I get back from that query is the account details. Right, so we're looking for one that has a certain username and password, and so it goes ahead and sends me back the object that is the matching account. I've also sanitized the passwords in the chain code. You might choose to approach that in a different way. I've just done that for brevity's sake here in this application. It also then, once we're logged in and have the account details, we can do other actions. So for example, we can say, hey, what are the tasks that need to be done, right? What's in the to-do list for this particular account? That's actually a separate account. A separate request. It's another query request against the blockchain, so it hits that query function in the chain code. And in this case, it's getting an argument that tells it to look for tasks for this specific account. And so these tasks come back. Here's an example of what I'm storing. So I have the account reference, the account ID, which is what we're using here. So 4B56F. Same thing here, 4B5. So that's the account mapping. That's really, think of that as a foreign key reference. And then whether or not the task is complete, when it was created, when it's due, how long it might take for me to accomplish this task, how much energy is involved in doing this task, the ID for the task itself, a location ID, so the different locations where I might want to do this to-do list task item, the name for the to-do list task item, the notes that I might want to have in it, and any kind of tagging that I might use for it. So if I wanted, for example, to implement some sort of search or other types of filtering down the road, I could certainly do that. So if we see this one is called chain all the things, and here is chain all the things, and so there's the one of the array of two, and then the other one is fix my daughter's toilet. So you got things to do. So in this case, we can see it's 4 days old. It's got awesome and journey as tasks. And I'll go ahead and expand it, and we can edit it. For example, I might remove the journey tag here, and when I click that, you'll notice that there's actually another transaction ID. So this is actually an invoke. I'm just updating the record. I already have a copy of the record myself here on the client, so I don't need any kind of real additional confirmation other than that the request was made. If you remember, we talked about consensus and other details around blockchain that will make sure that transaction happens in the right order. But when I call the invoke function in my chain code, I'm not getting any data back. What I'm getting back is this transaction ID. And if I go ahead and put that tag back in here, say journey, then you'll see another one pop up here. And again, I'm just updating the record at this point. And so it goes if I change this. So for example, April 1st is past due. So we'll say, hey, you know what, this is due Friday. And this has got to be done at work. So I'll go ahead and select work. It's going to take me, at this point, I'm just about wrapping up the day. So I'm going to take, this is going to take me about another hour to finish up. And normal energy works as well. And this is awesome because blockchain will revolutionize how you do business. Good to go. Maybe I want to have also record a video. There we go. So now I'm making those changes. And every time I make those changes, again, we're invoking the blockchain chain code to actually make changes to the data. Now what I'm going to do here, I'm just going to quickly kind of elaborate on some of the other features here. I can add a location where I might want to do my tasks or an actual task itself. These locations show up here. So for example, if I just wanted to know, hey, what can I do when I'm at the grocery store? So right now I don't have any things going on at the grocery store. What about at work? What can I do at work? Oh, I can chain all the things. What can I do at home? Right, so I can actually see, hey, I'm here. What can I do while I'm here? So what can I do at work in say 30 to 60 minutes? And any energy level will do. But let's say that I have a normal energy level. We have a real low on the energy level. There's nothing for me left to do, right? So just some kind of location and duration and energy filters here. We'll go ahead and switch those back to any. Now, what I'm going to do is actually move over the chain all the things here. Actually, let's do a new one. Let's do a new one. We'll say this is record the video. I'm going to pass this off to somebody else. So this is a journey video. Throw some tags in there. It's due today, so that's going to be important. And this is a work-oriented task, at least as far as I'm concerned. Probably take about an hour. And normal energy will be required. Record to-do list application. Good to go. So now we have that task. It's due today. I'm going to go ahead and forward it to Optin. So I'll forward it over to Optin, and it drops off of my list here. And that's all I need to do. So now I'm going to log out, and we'll log in as Optin. So I can log in as Optin. And here we go. Hey, record the video. It's the journey's the video to do today. And so he has all that here. It's now been assigned to him. And this is that example of having multiple parties involved, right? You have multiple writers involved. You want to keep an audit trail. You don't trust them with the data. You want to make sure that things can go back and forth in a secure fashion. And this is the benefit of blockchain, being able to hand things off back and forth. In this case, we don't really know if Optin is a member at my company. Maybe he's a video editing and production crew that we've outsourced, right? I don't know. It's not really important. Blockchain makes that possible for us to work between different companies securely. So in this case, we're going to say that he's going to finish, so we'll just go ahead and remove that task, and we're off to the races. And so now we have a web-based to-do list, blockchain-powered application. Pretty cool, right? All right, so if you want more, you can go out to the GitHub repository for this particular demonstration. It's github.com IBM to-do-list-fabric. Let's go ahead and close the development panel. There's a write-up on how this all works and the architecture and some of the diagrams you might need, how to get it deployed and running. So there's all kinds of great information in there for you. Of course, all the code you can review as well to see how all this works. I encourage you to play around with it. If you like it, you want to contribute to it, or want to see us out there showing this and talking more about this, maybe at a local meetup, let us know. Fork it, add a wiki, add an issue to get a presentation going, right? Make some changes, hit a pull request, let us know. All right. So now we're off to the races. Congratulations. Thanks for taking the time. And this is Kevin Hoyt, Developer Advocacy Lead for Emerging Technologies at IBM.